Okay, so then we can start with today's topic, which is, I'll start with classical gases. So now that we have developed the machinery of statistical mechanics, it's time to apply those to some simple and then some more real-life systems. Now, the rest of these lectures will be dedicated to these applications. First, I will start with some classical systems, and then we'll move on to some quantum systems. So, we already studied the fundamentals of classical mechanics last time. And today we are going to do a more, we're actually going to treat some systems. Sorry, I seem to have misplaced my my lecture, so let me bring up the right lecture. Yeah, awesome. So today, let's start with the partition function of some classical systems, okay? And let's, the microcanonical ensemble is just not very general enough. So what we will do is that we will be treating mostly the canonical example, the canonical ensemble. Okay. And once in a while, we'll also do a grand canonical ensemble. So let me remind you what does the canonical ensemble involve? It means that your system doesn't have any fixed energy, but it has some sort of fixed average energy, and it is interacting with some environment which sets its at some given temperature T. Okay. Now, suppose that our classical system, has Hamiltonian, and let's take like a one particle system. So the most simple classical system that we can take. Then its Hamiltonian would be given by P squared by 2m plus V of Q, right? Where V of Q is the potential that the particle is experiencing. Now, we talked about canonical ensemble before, and we discussed it in the context of quantum mechanics, even though I didn't explicitly mention it. But now we are going to translate it into classical mechanics. And the first question that we want to ask is that, what do we mean by the configurations, right? So the configuration of a classical system, how do we count that? We essentially count this by saying that if we are in the phase space, if you look at the phase space, then suppose we take a small volume of the phase space. This volume is, say, dq dp. Then what is the probability that our system is found in this volume? So according to the canonical ensemble, the partition function would be given by the exponential of the minus of the inverse temperature Kb times the energy, right? That would be a function of P and Q. Hamiltonian H is nothing but the energy function. And then we have to integrate it over all the possible configuration, that is the whole phase space. So we integrate over for one particle, it's just d cubed P and then d cubed Q. But note that the partition function is going to be nothing but the sum of probabilities, right? So this partition function needs to be dimensionless, but these guys have dimensions. Now it's very easy to show that the dimension of the integral here is the dimension of angular momentum cubed. So to make this guy dimensionless, we have to divide by something. And this something we are calling h cubed, where h has dimension of angular momentum. Okay? Now, the thing is that statistical mechanics is really about the microscopic nature of reality, right? And therefore, it's not surprising that for classical systems, for classical systems, you can derive, their partition functions from, say, taking some underlying, or the partition function of some underlying quantum system and taking their average. Okay, sorry, the wording is not very elegant. So you start with a quantum system, an appropriate quantum system, and then you take its average. When we say average, we actually is saying we are looking at some classical limit in some sense. That's how at some point we'll show how this partition function can be derived from a quantum partition function. If you look at that, if you look at the progeny of the classical partition function, that is, it's coming from quantum systems, then we can argue that this constant, which has the dimension of angular momentum, is nothing but Planck's constant. And in modern notation, it should be expressed as 2 pi h bar, right? Where h bar is the rationalized Planck's constant. Now everybody calls it Planck's constant. Okay, like this is what Planck called his constant, but then Dirac introduced h bar. Now you might say, okay, we are dealing with a classical system, but in the most central expression for the for this classical system, we have a quantum mechanical object playing in a central role. But remember that when we want to derive all the quantities in classical thermodynamics, we are actually taking derivatives of log of z. And therefore, any prefactor that we have is going to get separated because of the log. And then since we're taking some derivative, that prefactor, because it's a constant, it's going to drop out. So for all calculations in classical thermodynamics, Planck's constant is going to drop out. Okay. All right. Any questions? So there's going to be one place where h bar is not going to drop out, and that's when we compute entropy, right? Because if you remember, the expression for entropy was something like, what was it, kb d by dt t log of z, right? So there's going to be, because of the Leibniz property of the derivative, there's going to be one term where we have log of z without the derivative acting on it. And that is going to give us a result which depends on h bar. However, remember that in classical mechanics, in classical thermodynamics, we actually never compute the absolute value of entropy. In classical thermodynamics, we basically, what we do is that we just integrate, we integrate with respect, we just, in classical thermodynamics, the thing that we compute is the change in entropy always, right? This is what we compute from some state 1 to state 2. And therefore, any quantum effect, it cancels out from the integral. So we are never calculating the absolute value of entropy in classical mechanics, in classical thermodynamics. Okay.